What if everything you've ever known about life, every biology textbook, every classroom explanation about DNA, every scientific documentary you've seen was missing one fundamental truth, one cosmic piece of the puzzle that changes everything? Imagine, just for a moment, that the blueprint of your very existence, the spiraling code that determines the color of your eyes, the beat of your heart, and the workings of your brain, wasn't born in some ancient ocean or primordial soup on Earth, but rather came from somewhere far beyond it, perhaps carried through time and space on a comet older than the Sun, perhaps forged in the dark, cold nurseries between stars, or hidden in interstellar dust waiting for a planet like ours to catch it. Picture this: DNA, the molecule we associate with life itself, might not be native to Earth at all. And if that's true, then not only is life more ancient than our planet, it might also be far more universal, deeply embedded into the very fabric of the cosmos. This is not science fiction, it is a serious, growing field of study where astrobiologists, physicists, and chemists are uncovering baffling clues that suggest the story of our origin doesn't begin on Earth, but in the stars. Across decades, fragments of meteorites have crashed into our deserts and ice fields, revealing amino acids and organic compounds eerily similar to the ones found in every cell of your body. Telescopes and spectroscopes peering into interstellar clouds have detected complex carbon chains, ribose sugars, and precursors to RNA floating freely in the void. How is it possible that the building blocks of life compounds we once thought could only be formed in very specific conditions on Earth are not only common in space, but may have predated the Earth itself by billions of years? And what does that mean for us, for our origin story, for the assumption that we are a biological accident confined to a single rocky planet? For generations, science has offered a comfortable narrative that Earth, through random chance and time, assembled the molecules necessary for life, nurtured them, and eventually produced us humans capable of questioning the stars. But what if we got that backward? What if it was the stars, quite literally, that seeded the Earth with the raw instructions to build life? The idea isn't, Newsom call it, panspermia, the hypothesis that life, or its essential ingredients, traveled here from elsewhere, but recent discoveries are breathing new life into it, turning what was once fringe speculation into a serious conversation among experts. And here's where it gets strange. While we've found simple amino acids on meteorites, some researchers have stumbled upon structures that resemble sugars, nucleobases, and even chirality patterns in extraterrestrial material that match those in our own DNA. Chirality, the handedness of moleculesis vital to life as we know it, and Earth-based life uses only one specific orientation for amino acids. The odds of space randomly creating the exact same orientation aren't just low, they're astronomically low. So why do we find them out there? Could it mean that the life blueprint we carry isn't just Earth-specific, but part of some universal templatea, kind of biological architecture written into the cosmos itself? And if that's the case, are we alone? Or are we one expression of a much broader cosmic experiment? Think of the implications. If DNA or its components are not unique to our world, then perhaps life is inevitable wherever the right conditions exist, not a fluke, but a consequence of cosmic chemistry. Perhaps the universe is teeming with other beings, not necessarily human, but formed from the same alphabet of life, reading variations of the same ancient script. And maybe, just maybe, our urge to explore space isn't just curiosity, it's a form of cosmic memory pulling us back to where we came from. But the mystery deepens further. Some theories suggest that not only were the ingredients delivered here, but life itself may have already existed elsewhere and arrived intact, microbial, resilient, dormant, riding inside space rocks or on microscopic grains blown by solar winds. And if that's true, if life didn't just start here but arrived, then Earth is not the cradle, but the host, a stepping stone, a biological relay point in a much bigger galactic narrative. It's a staggering idea, one that forces us to rethink not just our past, but our future. Because if life came from space, if DNA is cosmic in nature, then understanding that journey could be the key to finding life elsewhere. Mars, Europa, Titanthes aren't just barren rocks, they're potential nodes in the same cosmic web. What we find there may not be foreign at all. It might be familiar, related, family. And here's the most mind-bending twist of all. Some researchers propose that certain viral fragments in our genome, bits of foreign code embedded in our DNA, might not have earthly origins either. Viruses are known to transfer genetic material between species. What if they've done that across worlds? What if part of your genome, the silent code tucked deep in your cells, is alien in origin, not metaphorically, but literally? It's a thought that challenges our sense of identity, but also expands it. Because if that's true, then to be human is to be a child of the stars, not just poetically, but biologically. And maybe the stars are watching us too. Maybe the great silence of the universe isn't because it's empty, but because it's waiting for us to realize we were never separate from it, that we've always been part of a greater whole. So if you've ever looked up at the night sky and felt something you couldn't explain, a pull, a strange nostalgia, a sense that you were staring at your origin, that feeling might be more than just imagination. It might be memory, and as science pushes forward, as we unlock deeper layers of our genetic code, as we scan the skies for signals and signatures, we might not just find alien life, we might find ourselves scattered across light years, waiting to be remembered. This story matters not just because it's fascinating, not just because it's strange, but because it speaks to something deep and universal in all of us, the need to know where we came from and what that means for where we're going. So if you're curious, if you feel that same pull, if you want to be part of the search for answers that might reshape everything from biology to philosophy, then you're in the right place. Like the video, subscribe to the channel, and drop a comment. Do you think our DNA is from Earth, or do you feel deep down that we've always been something more? For most of human history, the night sky was a canvas of mystery, dotted with lights that inspired mythology, religion, and fear. Early civilizations looked up and saw gods, stories, and signs, constellations etched into the heavens like messages from beyond. The Babylonians, Egyptians, Chinese, and Greeks meticulously tracked the movements of celestial bodies, believing them to influence the fate of kings, harvests, and empires. Yet despite their reverence and curiosity, the prevailing belief across much of the ancient world was geocentrism, the idea that Earth was the fixed, immovable center of the universe, with everything else revolving around it. This view, codified by thinkers like Aristotle and later Ptolemy, dominated Western thought for nearly 500 years. In this model, the cosmos was finite, composed of nested crystal spheres with stars embedded in the outermost shell, and heaven itself lay just beyond. It wasn't until the Renaissance that humanity began to seriously challenge this cosmic illusion. The 16th century marked a profound turning point with the work of Nicolaus Copernicus, who proposed a heliocentric model placing the Sun at the center and Earth as just another planet in orbit. Though his ideas were met with skepticism and resistance, especially from religious authorities, they laid the foundation for a scientific revolution. A few decades later, Galileo Galilei's use of the telescope provided empirical evidence supporting Copernicus. With his crude but revolutionary instrument, Galileo observed Jupiter's moons, phases of Venus, and the rugged surface of the moon, discoveries that directly contradicted the geocentric model. These revelations were not just technical achievements, they were existential shocks, showing that Earth was not the center of anything and that the universe was far more dynamic than previously imagined. As telescopic technology improved, so did our grasp of the cosmos. In the 17th century, Johannes Kepler refined planetary motion into precise mathematical laws, while Isaac Newton's Principia Mathematica in 1687 unified the heavens and the earth under a single framework: gravity. For the first time, the same force that caused an apple to fall could also explain the orbit of planets, weaving together the micro and the macro in a single cosmic thread. Still, even by the 18th and 19th centuries, the universe was thought to be relatively small and static, composed of stars confined to the Milky Way galaxy. It wasn't until the 20th century that the true scale of the universe and our tiny place within it was unveiled. One of the pivotal moments in this shift came from Edwin Hubble, who in the 1920s used observations from the Mount Wilson Observatory to demonstrate that spiral nebulae were not part of the Milky Way, but entirely separate galaxies. Even more shocking, he showed that these galaxies were moving away from us, with velocity proportional to their distanza discovery that led to the formulation of Hubble's law and the concept of an expanding universe. This marked the beginning of modern cosmology and lent strong support to the Big Bang theory, which posits that the universe began as a singular, incomprehensibly dense point some 13.8 billion years ago and has been expanding ever since. The implications of this discovery were staggering. Not only was the universe much larger than we ever imagined, but it also had a beginning of finite age that could be measured, traced, and understood. And with that understanding came a host of new questions. What came before the Big Bang? What lies beyond the edge of the observable universe? Is space infinite? Or does it curve back on itself? These questions pushed science into the realms of both philosophy and frontier physics. Technological leaps in the latter half of the 20th century accelerated our quest for answers. Satellites like the Cosmic Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, WMAP, measured the afterglow of the Big Bang, the cosmic microwave background radiation, with incredible precision, offering a snapshot of the universe when it was just 380 years old. These observations confirmed the Big Bang model and allowed scientists to fine-tune their understanding of the universe's shape, composition, and evolution. Meanwhile, quantum mechanics and general relativity, developed earlier in the century by pioneers like Max Planck and Albert Einstein, provided the theoretical scaffolding to explore the nature of space-time itself. Einstein's equations suggested a universe that was either expanding or contracting. Though he initially added a cosmological constant to keep it static, a move he later called his greatest blunder, especially after Hubble's discovery confirmed expansion. The concept of the observable universe emerged naturally from these new frameworks. Because light travels at a finite speed, approximately 299,792 kilometers per second, there is a limit to how far we can see, about 46.5 billion light-years in any direction. This boundary, known as the cosmic horizon, defines the observable universe. Beyond it, light hasn't had enough time to reach us since the beginning of time. But this doesn't mean that space ends there. It simply means we haven't seen what lies beyond. The observable universe is like a bubble around us, but the true universe may be much larger, perhaps infinite, or perhaps finite but unbounded, like the surface of a sphere in higher dimensions. The space age, beginning in the mid-20th century with the launch of Sputnik and culminating in the Apollo moon landings, added a visceral dimension to this intellectual journey. For the first time, humans were no longer passive observers of the cosmos, where we're explorers, touching other worlds, sending robotic emissaries to the outer planets, and extending our senses far beyond Earth. Telescopes like Hubble and missions like Voyager deepened our understanding, revealing not just the vastness of space, but its structure, superclusters, filaments, and voids, forming a cosmic web of unimaginable scale. The discovery of dark matter and dark energy in the late 20th and early 21st centuries further complicated the picture. Ordinary matter, the stuff of stars, planets, and people, makes up only about 5% of the universe. The rest is dark, invisible, mysterious, and poorly understood. Dark matter acts as an unseen gravitational glue, while dark energy appears to be driving the universe's accelerating expansion. These discoveries hint at a cosmos that is not only more complex than we imagined, but one in which most of its components are still invisible to us. Yet, despite our growing knowledge, a deep humility remains. We are observers on a small rock, circling a minor star in a galaxy among billions, peering into a darkness we can barely comprehend. Our instruments catch the faint whispers of distant explosions, the red-shifted light of ancient galaxies, and the subtle tug of gravity across cosmic voids. And still, we wonder. Still, we ask, what is the shape of the whole? Is it infinite, eternal, cyclical, or something stranger still? Are there other universes beyond our own, as some theories suggest an infinite multiverse where every possibility plays out, where every star you see is just a flicker in one of countless realities? The journey from geocentrism to multiverse theory is not just a history of scientific progress. but a testament to the expanding horizon of human thought. We began with stories to explain the stars, then used those stars to build the stories of science. And now, those stories are being rewritten again as we peer deeper into the universe's past and further into its structure. The historical context of our cosmic understanding is a tale of humility and a gradual unraveling of illusions, a relentless questioning of assumptions, and a breathtaking expansion of scale. Each milestone, from Copernicus to Hubble, from Galileo's telescope to the James Webb Space Telescope, has forced us to redefine who we are and what kind of universe we live in. And yet, with each answer, new questions are born. We now know that the universe is about 13.8 billion years old, born from a singularity, expanding ever since. We know that galaxies form and evolve, that stars live and die, that black holes lurk in their hearts, and that somewhere, perhaps even now, new worlds are being born. We know that we can only see a small fraction of what exists, and that even what we see is warped by gravity, time, and motion. We know that the cosmos is governed by elegant laws, but also riddled with mystery-dark energy, quantum uncertainty, the nature of time. The observable universe is not just a boundary of sight, but a metaphor for our knowledge itself, vast, growing, but forever constrained by what we can perceive. And yet, we keep pushing, keep asking, keep reaching into the dark. Because to understand the universe is to understand ourselves not just as a species, but as a moment in a cosmic story that is still being written. The stardust in our bones, the carbon in our cells, the hydrogen in our water, all of it forged in stars and scattered across galaxies, only to be reassembled into thinkers, dreamers, and storytellers. We are not merely in the universe, we are of it. And the story of how we came to know that step by step, century by century, is one of the most extraordinary journeys our species has ever taken. Imagine staring into the night sky, where each tiny star is a burning sun, possibly with planets of its own, and realizing that you are seeing not just light, but hysterophotons that have traveled millions, even billions of years to reach your eyes. In that moment, something shifts inside you, something primal and indescribable, a feeling older than language and deeper than reason. It's the moment your mind touches the edge of the infinite and brushes against the idea that you, with your memories and thoughts and fears, are somehow entangled in a story far larger than yourself. That feeling, part wonder, part terrorous. What makes this matter? Because this isn't just about science. It's about identity. It's about purpose. It's about belonging. If our DNA truly carries the signature of the cosmos, if the elements that make up our bodies were forged in ancient stars or delivered by interstellar messengers, then we're not just on Earth, we are of the universe itself. We are stardust that learned to think, to question, to dream. And that realization changes everything. It challenges the mundane. It cuts through the noise of daily life, the stress, the routine, the petty conflicts, and demands we pause and reconsider what it means to be alive. It asks us to see ourselves not just as individuals, or even as a species, but as participants in a vast and ancient dance of matter and energy, unfolding across scales so immense that they defy comprehension. But it also stirs something uncomfortable: fear. The fear of insignificance, of loneliness, of being adrift in a void so large and silent that we wonder if anyone or anything is listening. When we contemplate the cosmos, we're not just staring outward, we're reflecting inward, confronting our own fragility. The same stars that awe us can also remind us how temporary we are, how brief our lives, how easily we might be erased and forgotten in the churn of cosmic time. The Earth could vanish in an instant, and the universe would not blink. And yet, paradoxically, this terrifying scale can also be deeply comforting, because in that scale, our pain shrinks. Our problems, though real, are no longer the center of everything. We begin to see that life itself, any life, is extraordinary, precious, rare, a flicker of complexity in a sea of entropy. And perhaps, just perhaps, that makes it all the more meaningful. We care about this story because it reminds us that we are capable of caring about something bigger than ourselves. It shows that curiosity is not a luxury, it's a lifeline. It's what pulls us forward, generation after generation, from cave paintings to telescopes, from myths to mathematics, from survival to understanding. Children ask why the sky is blue, why the stars twinkle, why we exist at all. These aren't childish questions, they are the questions. They are the echoes of the oldest human yearning to know our place, to know if we are alone, to know if we matter, and the answers, as they unfold, connect us across time. When you learn that your body contains atoms formed in stars that died before the Earth was born, you're not just learning a fact, you're connecting to a lineage that spans billions of years. When you discover that every human shares nearly identical DNA, you're not just understanding biology, you're seeing the invisible thread that ties you to every person who has ever lived and ever will live. This knowledge doesn't diminish us, it dignifies us, it gives weight to our existence, and even more than that, it inspires us. Because if we are the universe made conscious, then our search for meaning, for beauty, for truth, is the universe exploring itself. What could be more profound than that? But let's not ignore the existential ache that often comes with this awareness. For many, the realization of the universe's scale triggers a deep sense of isolation. The cosmic void is not just out there, it's something we can feel inside us, especially when faced with the limits of human understanding. The silence of the stars, the vast dark between galaxies, can feel like a mirror to our own doubts and fears. What if we never find another civilization? What if our species never leaves Earth? What if we die without ever truly knowing why we lived? These are not easy questions, but they are real, and they deserve to be asked. And when we ask them, we discover that we're not alone in our wondering. Poets, scientists, philosophers, artists all have stared into the same abyss and tried to answer back. And maybe that, too, is a form of connection, a kind of cosmic companionship. Because while we may be small, we are not insignificant. Our ability to ask these questions is itself a miracle. Our consciousness, fragile though it may be, is the most complex thing we know of in the universe. And perhaps, in some strange way, that means we are important, not because the universe needs us, but because we give it meaning. Through our eyes, the stars are not just burning gas. Through our thoughts, atoms form dreams. Through our emotions, cold matter becomes love, fear, hope. We are not the center of the universe, but we are a center of experience, and that matters. That's why people should care, because in an age where attention is fragmented, where meaning is constantly questioned, and where the future feels uncertain, the cosmic perspective offers clarity. It shows us what endures. It shows us what's real. It invites us to zoom out, to see beyond borders, beyond politics, beyond conflict, and realize that we all share one fragile planet under one vast sky. It's a call to humility, yes, but also a call to greatness. A reminder that we are part of something bigger and that our choices echo far beyond our lifetimes. Whether we destroy ourselves or reach for the stars, whether we squander our brief moment or use it to build a better world, will determine what kind of story the universe tells about us. And that story is not yet finished. Every generation adds a sentence. Every breakthrough, every act of kindness, every question asked in wonder adds a word to the human chapter of the cosmic book. So when you look up at the stars tonight, let yourself feel it. All the awe, the fear, the beauty, the sadness, the longing, let it wash over you. Let it humble you, but don't turn away. Don't numb it, because in that feeling lies the truth of our condition, that we are small, yes, but capable of great things, that we are temporary but alive now, that we are one species, one planet, one chance, and that is enough. That is everything. This is why we search. This is why we care. This is why the mystery of our cosmic origin matters. Because it's not just about where we came from. It's about where we're going. It's about who we want to be. And in that journey, in that grand unfolding mystery, every one of us has a role to play. What if the next great scientific discovery didn't just come from a laboratory or a telescope, but from a simple question that you dared to ask? What if the mystery of our origin, the question of whether our DNA came from the depths of space or was born in Earth's earliest oceans, isn't something only scientists can explore, but something that each of us, in our curiosity, our wonder, and our willingness to engage, can help unravel? Pause for a moment and ask yourself, what do you believe about where life began? Do you picture bubbling primordial pools, lightning striking the early Earth, forming amino acids in a perfect storm of chemistry and chance? Or do you sense something more, something older, vaster, almost cosmic in its implications? Do you ever wonder why, of all the places in the universe, life ignited here? Is it a random accident or a trace of something much bigger, something the universe has done before and will do again? These are not questions with easy answers, but they are questions worth asking, because they strike at the very foundation of who we are. The mystery of our origins isn't just a fascinating puzzle for scientists, it's a lens through which we view everything: our purpose, our future, and even our ethics. If it turns out that life is not unique to Earth, that it's seeded across the galaxy or even beyond, then how should we see ourselves as a miracle, or as a single thread in a much grander fabric? Should we treat other planets as sacred, as potential cradles of life? Should we reconsider our place in the chain of being? Would we still see ourselves as the pinnacle of creation, or simply the latest chapter in an ongoing cosmic evolution? And what if, within the unexplored corners of our DNA, lie clues that tie us not just to Earth, but to the stars? What if that strange segment of genetic code that scientists don't fully understand, sometimes referred to as junk DNA, is actually a remnant of something ancient, alien, or even intelligent? It might sound like science fiction, but with every breakthrough in genomics, we discover just how much we still don't know about ourselves. Could it be that what we consider unknown is actually unrecognized pieces of a code we haven't yet learned how to read? And if so, what would it mean to decode it? Would we finally find our place in the universe, not metaphorically, but literally written into our biology? Think about that. Really think about it. If our DNA carries even a whisper of the cosmos, then we are not separate from the universe. We are its voice, its experiment, its dream. That changes everything. Now imagine a future where the mystery is solved, where we do find the clear signature of life beyond Earth, or trace our own molecules back to ancient meteorites with absolute certainty. How would the world react? Would religions adapt or fracture? Would nations unite or compete for the first extraterrestrial contact? Would our priorities shift from conflict to collaboration, from division to discovery? Would we finally realize that the only thing more important than being right is being curious together? Because in the search for answers, the process matters just as much as the outcome. It's not just about what we discover, it's about who we become in the act of discovering. These questions are not theoretical. The tools to explore them exist now. The James Webb Space Telescope is already peering into the atmospheres of distant exoplanets, hunting for biosignatures that could point to life. Laboratories around the world are simulating alien conditions, testing how life might form elsewhere. Space agencies are planning missions to icy moons like Europa and Enceladus, where subsurface oceans may harbor life today. And perhaps most exciting of all, AI and machine learning are being trained to detect patterns and anomalies in massive datasets, patterns that human eyes might miss, but that could represent the very clues we've been searching for. In this moment, right now, we stand on the edge of answers. We are closer than ever to knowing if life exists elsewhere or if it came from elsewhere. So what role will you play? Will you be a passive observer or an active participant in this unfolding story? Will you read and share, or will you think and question? Because your voice matters. Your questions matter. In a universe this vast, every mind turned toward discovery is a light against the darkness. And no question is too small. Why do we assume Earth is special? Why do we think intelligence is rare? Why do we limit our imagination to what we've seen, when the cosmos is filled with things we haven't even dreamed? Think about how different our world would be if we had the answers. How would school curriculums change if we confirmed alien biochemistry? How would philosophy evolve if we found organisms that challenged our very definition of life? How would art, music, and storytelling transform if we knew for certain that we were not alone? These aren't just scientific impacts, they're cultural, spiritual, existential. They ripple through every layer of what it means to be human. But even before we reach those answers, the search itself transforms us. It cultivates humility. It teaches us patience. It reminds us that not everything can be solved in a day, and that sometimes sitting with mystery is more powerful than having a solution. It reminds us that reality is not a fixed picture, but an evolving story, and we are the authors of the next chapter. So here's the invitation. Start asking. Ask in the comments. Ask your friends. Ask your teachers. Ask yourself, where do we come from? What are we made of? Are we alone? And don't just ask, listen. Listen to ideas that challenge you. Listen to stories that surprise you. Listen to theories that seem strange, because sometimes the truth hides in the unexpected. Join the conversation, because the questions we ask today will shape the discoveries of tomorrow. If you've ever looked up and felt the pull of the stars, if you've ever lain awake at night wondering if someone, somewhere, is looking back, then you already understand the importance of this mystery. It's not about aliens or spaceships, it's about meaning. It's about whether life is an accident or a design, whether we are fleeting sparks or pieces of something eternal. It's about the possibility that what we call human is just one form life can take, and that the universe has more stories to tell than we've dared imagine. And that should excite you. That should thrill you. That should make you want to dig deeper, read more, explore farther, because the unknown isn't empty. It's full of potential, and every time you engage with it, you become a part of the search. This is the heart of science, not the answers, but the courage to ask better questions, the curiosity to look beyond the horizon, the imagination to consider possibilities that don't yet fit within our models, and the willingness to be changed by what we find. So let's create a community of wanderers, of seekers, of explorers, not just of planets, but of ideas. Drop your theories, share your fears, post your wildest what-ifs, because in that chaos of thought lies the first flicker of truth. Maybe someone reading your comment will think of something no one else has. Maybe a child who watches this video will grow up to decode the mystery. Maybe the future Nobel laureate is out there, right now, reading these words and feeling that spark. That's the power of conversation. That's the power of community. That's the power of asking together, what if? So, comment below. Do you think life came from space? If we find out it did, what would that mean to you? And if you could send one message into the cosmos, one sentence that represents humanity, what would you say? Like, subscribe, share. Not because the algorithm demands it, but because these questions matter. Because somewhere, out there, the universe is waiting to be understood. And we are the ones who must rise to the task. Let this be the generation that dared to wonder, that reached not just for answers, but for each other. That turned the cosmic mystery into a global conversation. Because the greatest discoveries don't just change our knowledge, they change us. And the first step is asking a question. What will yours be? Far above the hum of city lights, beyond the scattering clouds and the thin blue veil of Earth's atmosphere, stretches a vast, cold, silent realm that defies imagination. It begins where air becomes vacuum and light no longer scatters, where day and night lose their meaning, and the human eye, unshielded, would witness a canvas so ancient and enormous that words like big or old lose their power. Here, in the heart of the cosmos, galaxies swirl like frozen whirlpools, each one a sprawling congregation of stars, gas, dust, and mystery. Hundreds of billions of suns coalesced into luminous spirals and ellipticals, drifting slowly through the black ocean of space-time. Between them lies the void, not emptiness in the human sense, but regions so vast and underpopulated that entire clusters of galaxies could vanish into them without a trace. These voids are not simply gaps in the map, they are part of the structure itself, forming with filaments and superclusters the great cosmic web, a scaffold of matter that stretches across the observable universe like a ghostly fingerprint of creation. Amid this grandeur, stars are born in stellar nurseries-dense clouds of gas and dust collapsing under their own gravity, heating, igniting fusion, and giving rise to newborn suns. Some of these stars form binary systems, others launch planets into orbit, and around some of those planets, perhaps, the same story of chemistry becoming biology begins to unfold. Supernovae erupt in brilliant flashes, momentarily outshining entire galaxies, and from their violent deaths scatter heavy elements iron, gold, carbon-seeding space with the ingredients for future worlds. At the center of many galaxies lurk supermassive black holes, invisible engines of destruction and order, bending time and space with such intensity that nothing, not even light, can escape. Yet from these gravitational monsters pour jets of energy and radiation that shape galactic evolution, regulating the birth of stars, influencing matter across millions of light years. And around all of this, every star, every planet, every cloud of hydrogen lays something stranger still: dark matter, an unseen scaffolding that binds galaxies together, outweighing visible matter by a factor of 5. Though it emits no light and interacts with normal matter only through gravity, its presence is undeniable, betrayed by the motion of stars at the edges of galaxies and by the warping of light across cosmic distances. Its origin remains one of the greatest mysteries in modern physics. Is it composed of yet undiscovered particles? Is it a flaw in our understanding of gravity itself? And surrounding even that, in the deepest, darkest corners of our knowledge, is dark energy, an unknown force that appears to be accelerating the expansion of the universe, stretching space itself apart faster and faster, as if the fabric of reality is being pulled taut by invisible hands. To gaze into space is not to look at something distant, but at something timeless. The light from the Andromeda Galaxy, our nearest galactic neighbor, takes over 2 million years to reach us, meaning we see it not as it is, but as it was before Homo sapiens ever walked the Earth. And yet, within this delay, this slow dripping of cosmic light into our instruments and eyes, lies the beauty of astronomy. To look up is to look back, to peer into the history of the universe itself, layer by layer, epoch by epoch, from the first stars igniting in darkness to the grand spirals of mature galaxies, spinning gracefully in the gravitational embrace of invisible mass. In this theater of light and shadow, of seen and unseen, stand the key players of cosmology, the scientists and thinkers who have dared to describe the indescribable. Albert Einstein, whose equations of general relativity first suggested that space could bend and time could stretch, gave us the mathematical language to model the dynamic universe. Edwin Hubble, who observed the redshift of distant galaxies, showed us that the universe is not static but expanding, with every galaxy moving away from every other like raisins in rising dough. Vera Rubin, measuring the rotation of spiral galaxies, provided the first clear evidence that dark matter must exist, even if we still don't know what it is. Georges Lemaitre, the Belgian priest and physicist, first proposed what would become the Big Bang Theory, a universe born from a single point, a primeval atom, expanding outward into time and space. Later, teams of scientists built upon these ideas with satellite missions like COBE, WMAP, and Planck, measuring the cosmic microwave background, the faint afterglow of the Big Bang itself, now cooled to just a few degrees above absolute zero. This radiation bath, uniform and isotropic with tiny fluctuations, gives us a baby picture of the cosmos when it was just 380 years old, long before stars or galaxies had formed. A time when light first escaped the plasma of the early universe and began its journey to us. From these subtle temperature differences, cosmologists have derived the shape, age, composition, and fate of the universe. It's not just theoretical, it's mapped, it's measured, it's real. And still, questions persist. Are we in a flat universe, destined to expand forever, growing colder and emptier with time? Or is there a hidden curvature, a deeper topology, a larger multiverse, beyond our own visible domain? Are black holes gateways to other regions of space or time? Can gravity be unified with quantum mechanics into a single elegant theory of everything? These aren't idle speculations, they're the active frontiers of scientific inquiry, and teams around the globe are racing to explore them. Particle physicists at CERN smash atoms to glimpse the conditions of the early universe. Radio astronomers build telescope arrays like the Square Kilometre Array to listen for whispers from the cosmic dawn. Gravitational wave observatories like LIGO and Virgo detect the tremors of colliding black holes and neutron stars, turning spacetime itself into an instrument. Yet for all our instruments and models, the tone of this exploration remains one of awe, humility, and deep curiosity. The more we learn, the more mysterious the universe becomes. Each new answer opens a dozen new questions, like a fractal unfolding into deeper and deeper layers of reality. It's as if the universe is a story written in a language we are just beginning to understand, a story with characters we haven't met, themes we haven't guessed, and an ending we cannot yet foresee. And within that story, perhaps our greatest role is not to control, but to listen, to watch, to learn. Because the cosmos doesn't owe us meaning, but it offers us the chance to create it. To build atmosphere in this story is not just to describe distant galaxies or invisible particlets, to create a mood of reverence for the unknown. It's to feel the chill of the cosmic night, the thrill of discovery, the silence between stars that invites our questions, our hopes, our fears. In this silence, we remember that we are not spectators, we are participants. Our thoughts, our instruments, our questions, these are the tools by which the universe becomes aware of itself. We are the edge of the cosmos, thinking about its own edge. We are the flash of consciousness in a sea of entropy. And that idea, more than any measurement or calculation, gives this story its emotional weight. So imagine standing on the surface of a distant moon. Earth, a pale blue dot in the sky, surrounded by the rings of Saturn or the shadows of icy craters. Imagine drifting through interstellar space, past rogue planets and comets shaped like relics from forgotten times. Imagine looking into a nebula where stars are being born, or falling toward the event horizon of a black hole where time slows and space warps. These are not just science fiction fantasies, they are future destinations, real places in a real universe, awaiting real explorers. And perhaps the first step on that journey is not physical, but mental. A shift in perspective, a willingness to wonder. Because the atmosphere of the universe is not made of air, it's made of questions. It's made of silence and signals, of explosions and expansion, of invisible forces sculpting the visible world. And in that atmosphere, the human mind floats, small but luminous, a flame in the dark reaching always upward. From the earliest moments of astronomy, when ancient stargazers tried to map the heavens with naked eyes, to today's sprawling observatories scanning the skies in radio, infrared, and X-ray wavelengths, humanity has always been driven by one question: what lies beyond? Beyond the stars, beyond the galaxies, beyond the known limits of space, what, if anything, waits at the true edge of the universe? And yet, the deeper we peer into the abyss, the more it seems that the answer may be forever out of reach. The very notion of an edge begins to blur the further science progresses, not because the universe lacks boundaries in some childish way, but because the reality is far more complex and possibly paradoxical. There are signs, buried within our most precise equations and boldest theories, that suggest we may never truly find the edge of the universe. Not because it doesn't exist, but because we might be fundamentally incapable of perceiving it. It begins with light. The speed of light, an unbreakable barrier in our current understanding of physics, means that we can only observe a finite portion of the cosmos. We call it the observable universe, a sphere centered on Earth with a radius of about 46.5 billion light-years. But that's not the edge. That's just how far light has traveled since the Big Bang. Beyond that lies more universe, possibly much more, but we cannot see it, cannot measure it, and may never interact with it. That limit is not arbitrary. It's built into the structure of reality itself. If the universe is expanding faster than the speed of light between certain distant regions, then those regions are receding from us faster than light can close the gap, and they become causally disconnected. That is the first and most immediate wall we hit, the cosmic event horizon, a boundary not of space, but of information. There could be galaxies, even civilizations, beyond that horizon, but they are lost, to us not temporarily, but permanently. In a way, they exist in a parallel timeline, a separate chapter we can never read. Then come the paradoxes, the signs that our models may be incomplete or even fundamentally flawed. Quantum mechanics, with its probabilistic haze and spooky entanglements, describes the microworld with astonishing precision, while general relativity governs the macro with elegant curvature and deterministic force. But the two don't speak the same language. When applied to extremes like the singularity at the heart of a black hole or the moment of the Big Bang, these theories collapse, yielding infinities and undefined behaviors. These are not just mathematical headaches. They are indicators that we may be missing something essential, a deeper theory yet to be discovered that reconciles the quantum with the cosmic. Until then, any attempt to describe the edge of the universe must confront the possibility that our tools are insufficient. We're using two incompatible maps to explore a territory we've never visited. Add to this the unsettling implications of inflation theory, which posits that in the first fractions of a second after the Big Bang, the universe underwent exponential expansion, ballooning faster than the speed of light. This inflation may have been patchy, with different regions inflating at different rates, or ceasing inflation at different times, leading to the multiverse hypothesis, a scenario in which our universe is just one bubble in a vast cosmic foam. If true, then asking about the edge of our universe is like asking for the edge of a single soap bubble drifting in a never-ending bath. The edge would not be a wall, but a transition into another universe with different laws of physics, unreachable by any known means. It's a powerful and elegant idea, but also a chilling one. Because if the multiverse exists, we may never find a way to confirm it. The physics of other regions could be so alien that their signals wouldn't even register with our instruments. And if that's the case, then the ultimate frontier may be not physical but epistemological, a limit not on where we can go, but on what we can know. We also face limitations in our ability to interpret the data we do have. Observing the universe is not like reading a book, it's like reconstructing the plot from burned and scattered pages. Light from distant galaxies is stretched and reddened by the expansion of space, distorting the information it carries. Gravitational lensing bends light around massive objects, creating illusions and mirages on the grandest scale. Cosmic microwave background radiation, once our clearest window into the early universe, now appears with subtle anomalies, temperature variations, cold spots, asymmetries that don't quite match the standard model. Are these statistical flukes, measurement errors, or hints of physics beyond our current understanding? No one knows for sure. But each deviation whispers that the story we've built so far may have missing chapters. And then there's the unsettling discovery that the expansion of the universe is accelerating, driven by an unknown force we call dark energy. This force accounts for nearly 70% of the universe's total energy content, yet we have no idea what it is. It might be a property of space itself. It might be a dynamic field. It might be the first hint of a breakdown in general relativity on large scales. But until we understand it, our models of the universe's future, and by extension, its true shape and extent remain speculative. If the expansion continues to accelerate indefinitely, then galaxies will eventually drift so far apart that even their light won't be able to reach us. The night sky will go dark, not because the stars have died, but because their light has been stretched beyond visibility. In that lonely future, the cosmic edge won't be a placet, will be an experience. A slow fading of everything we once knew, until the observable universe contains only the dying embers of our own galaxy. In this context, the pursuit of the edge becomes a philosophical challenge as much as a scientific one. What does it mean to seek a boundary that may not exist in space, but in perception? Can we be satisfied with understanding part of the story, knowing that the whole may lie forever beyond our reach? Or will we, like generations before us, continue to push outward, even if the horizon moves with us always receding, never caught? That tension lies at the heart of cosmology. It is both its fuel and its heartbreak. Every discovery brings us closer to the truth, and every discovery reveals how far we still are. This conflict, the one we are foreshadowing, was not a battle between scientists or theories. It is a struggle between knowledge and its limits, between the light of human curiosity and the shadows cast by nature's deepest secrets. It plays out not in headlines or popular science books, but in equations written on whiteboards, in sleepless nights spent staring at anomalous data, in mission failures and breakthroughs. in debates between those who believe the universe is knowable and those who caution humility. The true edge, perhaps, is not spatial at all. It may be the edge of comprehension, the line where human cognition meets the vastness of what is. And that line moves not because the universe resists understanding, but because understanding changes us. With each expansion of knowledge comes a reshaping of the self, and sometimes that reshaping reveals how much we've misunderstood. And yet, despite this looming uncertainty, the pursuit continues. Scientists build more sensitive detectors, more powerful telescopes, more refined simulations. The James Webb Space Telescope is already offering data from the earliest galaxies, breaking records, challenging assumptions about how quickly structure formed after the Big Bang. Quantum physicists are probing entanglement and holographic principles that might one day connect gravity and information in a unified theory. Theoretical physicists are exploring brane worlds, string theory, and quantum gravity scenarios that might peel back the veil hiding the universe's birth and edges. And amateur SARE, scanning the sky, classifying galaxies, identifying anomalies, contributing to the collective effort. Because even if the edge remains elusive, the journey itself is transformative. So, when we ask whether we will ever find the true edge of the universe, we must ask ourselves what kind of edge we mean. A physical boundary? A moment in time? A limit to perception? A break in the laws of physics? Or is it the edge of imagination itself, the place where wonder collides with the unknowable? These questions, layered and shifting, are the prelude to the conflict that drives the narrative forward. They are the tension that fuels every chapter of cosmic exploration. They are the warning that not all mysteries end with answer sand, that sometimes, the deeper we go, the more lost we feel. But that, perhaps, is the greatest sign of progress. To feel lost is to realize how far we've come from certainty. To feel challenged is to remember that the universe owes us nothing but that we are still brave enough to ask. So we continue, uncertain and unsatisfied, yet undeterred. We search the sky, map the dark, write new models, test them, break them, rebuild. We measure the fluctuations in the microwave background. We trace the redshift of galaxies. We detect the echoes of gravitational waves. And still, the edge remains near, but unreachable. Visible, but veiled. Real, but not quite touchable. This is not failure. It is the beginning of conflict. The quiet tension between what we know and what we can never know. And it is there, in that fragile, shifting border, that the story truly begins. In the heart of modern cosmology lies a fundamental conflict, not a clash of egos, but of ideas, of frameworks so vast and so opposed that reconciling them seems almost impossible. It is the tension between the observable and the theoretical, between what we can see and measure and what the math tells us must be true. And at the core of this battle is the question that has haunted both scientists and philosophers alike for centuries. Does the universe have an edge? Is it infinite, stretching endlessly beyond what we can detect? Or is it finite, curved in on itself like a cosmic loop, vast yet bounded? Every answer spawns new questions. Every theory is a lighthouse in the fog-guiding, but never fully illuminating the truth. The conflict is alive in debates, research papers, and midnight calculations, where the most brilliant minds of our generation argue not over trivial details, but over the very shape of reality itself. On one side of the battlefield stands the infinite universa model, elegant in its simplicity, supported by the idea that space, uncurved and flat, expands forever. According to this view, there is no center, no edge, no boundary where the universe ends or folds back. Galaxies go on forever, and even though we can only see a portion, the rest exists just the same, unseen, but real. This model aligns well with general relativity and the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. It suggests a universe without privileged locations, where every observer sees roughly the same thing, and the laws of physics are consistent throughout. But then, on the other side, stands the finite model. Here, space is curved, not metaphorically, but geometrically, shaped by mass, energy, and the expansion rate of the cosmos. This universe might be closed, like the surface of a sphere, looping back on itself in higher dimensional space. Travel far enough in one direction and, given enough time and the right path, you might return to your starting point. In this view, the universe still has no edge and no wall where it ends, but it is bounded. There is only so much space, so much matter, so much room for galaxies to form and time to unfold. The idea is both thrilling and claustrophobic, a cosmic hall of mirrors where everything eventually connects. Between these two extremes lies a range of hybrid possibilities. A flat yet infinite universe that's expanding, a finite universe with positive curvature, a universe with hidden dimensions rolled up so tightly they're imperceptible to us. The mathematical tools to explore these models manifolds, tensors, topological space are dizzyingly abstract, but the implications are deeply human. If the universe is infinite, then every possibility may already exist somewhere. If it is finite, then the total amount of matter, energy, and information is knowable in principle, even if not in practice. Either way, we are forced to confront the limits of observation. Our telescopes can only reach so far. The cosmic microwave background is a veil we cannot see beyond. The speed of light, the expansion of space, the age of the universe, all these impose hard ceilings on what we can measure. And yet, cosmology is not content with what is merely measurable. Theoretical physics demands consistency. Quantum mechanics and general relativity, the two great pillars of 20th century science, cannot yet be fully reconciled. Each works brilliantly in its own domain, but they crumble under pressure when forced to describe the same extreme conditions. Black holes, for instance, should obey both sets of rules, but their internal mechanics remain a paradox. The edge of the universe, especially in the earliest moments of the Big Bang, is subject to the same contradictions. Did time have a beginning? Was there a before? Did space emerge from a singularity? Or was it born through a transition from a previous state? Inflation theory, string theory, loop quantum gravity offers answers, but none have achieved consensus. Inflation theory, widely accepted among cosmologists, holds that the universe expanded exponentially in a fraction of a second after the Big Bang, smoothing out irregularities and explaining the large-scale uniformity we observe today. But this very theory leads to its own conflict. If inflation never completely stopped in some regions, then new bubble universes are constantly being formed, each with its own physical laws, its own constants, its own matter and energy. This is the multiverse, a concept that fractures the notion of a single, unified cosmos. Some physicists embrace this as the natural consequence of inflation. Others reject it outright, arguing that it's untestable and therefore unscientific. The clash is not just about numbers, it's about the soul of science. Should we accept elegant ideas that can never be verified, or stick to what we can measure, even if it leaves major questions unanswered? Meanwhile, the struggle to define the edge continues to evolve. To some, the edge is temporal, the beginning of time, the moment of the Big Bang. To others, it is spatial, the boundary of the observable universe, or the ultimate limit of expansion. Still, others think of it as energetic, the boundary, beyond which particles and forces behave differently, governed by physics we have not yet discovered. In each case, the edge is elusive. It recedes as we advance. We send satellites farther. We peer deeper into the infrared. We model earlier and earlier moments after the Big Bang, but the edge never stays still. It's not just far away. It's moving away, faster than we can catch it. Compounding the conflict is the tension between theory and observation. The Lambda CDM model, the current standard cosmological model, predicts a universe dominated by dark energy and dark matter. Yet, we have never directly detected either. We infer their presence through gravitational effects and cosmic measurements, but they remain invisible. Some argue that our understanding of gravity itself might be flawed, that perhaps a modified theory of gravity could explain what we now call dark. Others warn against discarding a model that works so well at large scales just because of local mysteries. The debates are fierce, the data hotly contested, the interpretations deeply personal, and all of it feeds the central conflict. We know so much, yet we do not agree on what it means. In academic circles, this tension manifests in research papers, conferences, and competing grants. Theorists propose exotic models. Observational astronomers demand data. Instrumentalists design ever more sensitive detectors. Philosophers of science weigh in on what it means to know something about the cosmos. The field is collaborative, yes, but also competitive. Careers are built on the defense of one model over another. Entire missions are designed around specific hypotheses, and the truth is, no one knows which model will win, if any ever will. Perhaps the universe is stranger than we can imagine, governed by rules that elude our best minds. Or perhaps the answer is just around the corner, waiting for the next breakthrough to tip the scales. In this chaotic landscape, one theme emerges: uncertainty. Not ignorance, but a profound awareness of the complexity of nature. The conflict is not a failure, it's a sign of progress. It means we are reaching the boundaries of current knowledge. It means we are asking the right questions. Should the universe have an edge? Or is edge a meaningless concept in four-dimensional space-time? Is the cosmos a self-contained system, or part of something larger? Is our patch of the multiverse unique, or one of infinite variations? These questions don't paralyze science, they fuel it. They drive the search for new models, new data, new philosophies. But they also create emotional and intellectual strain. For cosmologists working at the cutting edge, the conflict is deeply personal. It means devoting decades to an idea, only to see it upended by new evidence. It means standing before audiences and defending a theory, knowing that tomorrow it may be disproven. It means confronting the possibility that some answers may never come. That the universe might be infinite in both size and mystery. That the edge, if it exists, may lie forever beyond our reach, not because we are too small, but because reality is too large. That's the true nature of this conflict. It is not a war between scientists. It is a struggle between the limits of human understanding and the endless complexity of the cosmos. And yet, this very struggle is what makes the field so alive. It's why students devote their lives to equations they may never solve. It's why telescopes are built on mountaintops and satellites launched into the void. It's why we argue late into the night, why we revise our models, why we dare to dream of a unified theory. Because even in conflict, there is hope. Hope that through the fog of paradoxes and contradictions, a deeper truth waits. One that doesn't choose between infinite and finite, but reveals a structure more subtle than either. One that doesn't just answer our questions, but transforms how we ask them. The universe is not obligated to make sense to us, and yet, against all odds, it often does, at least in pieces. That we have mapped the stars, measured the cosmic background, detected gravitational waves, nothing short of miraculous. And still, the conflict continues. The edge is out there, or it's not. The universe is finite, or it isn't. Space is flat, or curved, or twisted in ways we cannot yet imagine. Theories rise, observations push back, models fracture and reform. And in that dance, in that beautiful, relentless conflict, lies the heartbeat of cosmology. If the universe has no edge, if it stretches on forever, without boundary or limit, if there is no final wall, no outer shell, no place where space ends and something else begins, then we are standing at the brink of one of the most profound and destabilizing truths humanity has ever confronted. The idea of an infinite universe isn't merely a geometric curiosity or a mathematical model. It is a conceptual revolution, one that shakes the foundation of what we believe about existence, origin, and meaning. It rewrites the assumptions not only of cosmology, but of philosophy, spirituality, and the story of what it means to be human. A universe without an edge challenges us not just scientifically, but existentially. And in doing so, it reveals the limits of our current physics and demands a new way of seeing everything from the smallest particles to the structure of space itself. From the perspective of physics, an infinite universe raises immediate and complex questions. In a cosmos without boundaries, how do we define total energy? Can such a universe even be stable? Does infinity imply eternal repetition and endless recurrence of patterns, of galaxies, of life itself? In a truly infinite space, every configuration of matter not only happens, but happens an infinite number of times. Somewhere out there, there may be an exact duplicate of you, living a life identical in every way up to this moment. And beyond that, a version of you who chose differently, failed differently, triumphed differently. If the universe has no edge, then every possible outcome is not only possible, it is inevitable, recurring eternally in a cosmic landscape too vast for imagination. This idea, sometimes called the infinite multiverse, transforms identity and uniqueness from absolutes to illusions. Who are you if there are endless versions of you living out every possible path your life could take? But even before we reach such dramatic implications, infinite space raises problems for our models. General relativity, which describes gravity as the curvature of spacetime, works beautifully on large scales, but it does not handle infinities well. In fact, whenever infinite values appear in our equations, it is a red flag, a sign that our theory has hit a boundary of its applicability. Singularities, like those at the center of black holes or at the Big Bang, are where spacetime curvature becomes infinite and general relativity breaks down. Similarly, if space is truly infinite, then the total mass and energy of the universe would also be infinite, making many of our current calculations, based on finite quantities, either meaningless or impossible. We can model patches of an infinite universe, but we cannot account for its totality. Our mathematics is local. Infinity is not. This mismatch suggests that our theories, as powerful as they are, may be fundamentally incomplete. Enter quantum mechanics, the other pillar of modern physics. Unlike general relativity, quantum theory handles infinities differently, often subtracting them out through a process called renormalization. But even quantum field theory, which describes particles and their interactions with astonishing precision, struggles when confronted with the infinite expanse of spacetime. The vacuum energy predicted by quantum mechanics, for instance, leads to a value for the cosmological constant that is 10 nu 2 times greater than what we observe, arguably the worst prediction in the history of science. This discrepancy suggests a fatal flaw in our understanding, a clue that something deeper is missing. The merging of quantum mechanics with gravity into a single theory, quantum theory of spacetime, is one of the great unsolved problems in physics. And it is impossible to complete without reckoning with the shape, size, and structure of the universe itself. If the universe has no edge, then any final theory of everything must be compatible with the infinite. And so far, none are. The philosophical implications are just as staggering. A universe without an edge is a universe without a center, without a preferred location, without a beginning or an end that we can reach. This challenges not only scientific assumptions, but also cultural and religious narratives that place humanity at the heart of creation. If the cosmos is infinite, then Earth is not special. It is not even rare. It is one of uncountable islands in a sea of stars, one configuration among endless variations. This does not diminish our value, but it recontextualizes it. It forces us to see ourselves not as the climax of existence, but as a moment within an ongoing, possibly eternal process. And that shift can be both terrifying and liberating. Terrifying because it dissolves the illusion of cosmic centrality. Liberating because it invites us to participate in something far greater than ourselves. In many ways, the idea of an infinite universe resurrects ancient philosophical questions. The Greeks debated whether the cosmos was finite or boundless. Medieval scholars wrestled with the nature of the firmament and whether space could go on forever. Now, with telescopes and satellites and particle accelerators, we face those same questions, but with data. And the data is confusing. The universe appears flat on large scales, which suggests it could be infinite. But it also could be so large and subtly curved that its curvature escapes our detection. We measure what we can, we model what we know, but we cannot yet confirm the whole. And so, we live in tension between a universe that feels infinite and models that cannot fully handle it, between the dream of total knowledge and the reality of bounded perspective, between the yearning to know the edge and the possibility that there is no edge to find. This is not a failure of science, it is its frontier, but it also exposes the need for new physics. Not just extensions of current models, but revolutions in how we understand reality. Concepts like the holographic principle, which suggests that the universe may be a projection of information encoded on a distant boundary, hint at radically new frameworks. So do ideas from string theory, loop quantum gravity, and emergent spacetime. Each of these approaches tries, in its own way, to explain how the universe could be both boundless and bounded, both finite and infinite. And each reveals how far we have to go. The existential weight of all this is hard to ignore. If the universe has no edge, then there is no outsidino higher vantage point from which to observe the whole. We are inside the totality. We are the experiment. We are the phenomenon trying to understand itself from within. This is exhilarating. It is also deeply humbling. It means that our search is unending, not just practically, but philosophically. That there may always be more to learn. That knowledge is not a destination, but a path. And that the unknown is not a failure of understanding, but a feature of existence. For individuals, this can inspire either awe or despair. Awe at the beauty and grandeur of a cosmos without limits. Despair at the possibility that we are lost in an endless sea with no ultimate purpose or plan. But perhaps there is a third response, one rooted in acceptance and wonder. To live in an infinite universe is to be free of boundaries, to be part of a story that has no end, to know that even if we cannot see the edge, we are still part of the whole, and that our thoughts, our questions, our science, however locale, resonate into that vastness. They matter, not because they complete the picture, but because they add to it. The consequences of this conflict between the dream of finding the edge and the reality of its possible absence are not just academic. They shape how we fund science, how we teach cosmology, how we imagine the future. They influence the design of telescopes, the priorities of space missions, the direction of theoretical research. They determine which questions we ask and which we set aside as unknowable. And they ripple outward into culture, shaping how we see ourselves in the universe. If we embrace the idea of a universe without edge, we must also embrace a new kind of science, a science that acknowledges its limits without surrendering to them, a science that seeks understanding, not control, a science that is comfortable with mystery. This is not easy. It requires intellectual courage, it requires humility, and it requires a new language, one that blends the mathematical with the poetic, the empirical with the existential. Because the infinite is not just a number. It is a feeling. It is a perspective. It is the realization that the universe is not a puzzle to be solved, but a conversation to be joined. So, what do we do in the face of this truth? We keep going. We keep asking. We keep building better instruments, writing better theories, teaching the next generation not just to know, but to wonder. Because even if the universe has no edge, we do. Our time is limited. Our minds are finite. But in those finite minds burns the light of curiosity, and that light reaches farther than we ever imagined. It touches galaxies. It touches atoms. It touches the deep structure of space and time. And maybe, just maybe, that light is the closest thing we'll ever get to finding the edge, not in space, but in ourselves, in the boundary between what we know and what we dare to dream. In that sense, the conflict is not about the cosmos at all. It's about us and what we choose to become in the face of the infinite. There comes a moment in every great journey where the old map no longer serves, where the lines that once marked the edge of the known world vanish into ambiguity, and explorers must either retreat or step boldly into the unknown. In the story of cosmology, that turning point has already arrived, not once, but in waves, each one crashing against the walls of our understanding and leaving behind fragments of a new reality. From the expanding universe to the strange repulsive force we now call dark energy, from the incredible eyes of space telescopes to the ever-growing precision of particle physics, the 21st century has brought with it not just new discoveries, but a deepening sense that we are on the cusp of something larger, something that may redefine our place in the cosmos yet again. One of the most transformative revelations came not from a bold new theory, but from an unexpected observation. In the late 1990s, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure how fast the universe's expansion was slowing down. According to everything we understood about gravity, the mass of all galaxies, stars, gas, and dark matter should be pulling on each other, gradually decelerating the cosmic expansion that began with the Big Bang. But what they found defied all expectations. The light from distant Type Ia supernovae wasn't dimmed in a way that indicated slowing expansion. Instead, it suggested the opposite. The universe's expansion wasn't slowing, it was accelerating. This revelation was the moment the floor dropped out from under our theoretical models. Something was not just counteracting gravity, it was overpowering it, driving galaxies apart faster and faster with each passing second. The name given to this mysterious force was dark energy, a placeholder term for an unknown agent that makes up nearly 70% of the total energy content of the universe. Overnight, our understanding of the cosmos changed. The universe wasn't just getting older, it was getting faster, bigger, and darker. And that realization forced a re-evaluation of everything, from the fate of the cosmos to the very structure of space-time. Dark energy became a central character in the cosmic narrative. If its influence continues indefinitely, galaxies will eventually recede beyond each other's observable horizons, stars will fade, and the universe will approach a state of cold, dark isolation, a scenario known as the Big Freeze. But if dark energy evolves over time, or if it's part of a deeper dynamic field, other outcomes become possible. A big rip, where the fabric of space-time is torn apart, or a cosmic rebound that gives rise to a new cycle. Each of these possibilities depends on the nature of dark energy, a substance we have never directly detected, only inferred through its effects. Its discovery marked a turning point not only in cosmology, but in our relationship with the unknown. It proved that even in an age of extraordinary scientific sophistication, nature could still surprise us in ways that rewrite the textbooks. To chase the ghost of dark energy and the deeper structure of the universe, became clear that better tools were needed. Enter the new generation of space telescopes and ground-based observatories, technological marvels that see farther, clearer, and in more wavelengths than anything before. The Hubble Space Telescope, once the pinnacle of human observational power, began to hand the torch to successors like the James Webb Space Telescope, which peered into the infrared to reveal the first galaxies that formed after the Big Bang. Where Hubble showed us a universe of stunning beauty, JWST unveiled one of complexity, motion, and depth, faint galaxies forming earlier than expected, dusty star nurseries shaping planetary systems, and ancient light traveling for over 13 billion years to reach our instruments. And JWST was just the beginning. Telescopes like Euclid and the Nancy Grace Roman Space Telescope were designed specifically to map the influence of dark energy across cosmic time. They would study the way galaxies cluster, how light bends around massive objects, and how the universe's expansion history changes over billions of years. These missions were born from the need to understand not just what the universe looks like, but how it behaves. And their findings have already begun to reshape expectations. Some measurements have shown tension small but persistent deviations between predicted and observed values, particularly in the rate of cosmic expansion known as the Hubble constant. The Hubble Space Telescope and JWST suggest one value. The cosmic microwave background, as measured by the Planck satellite, suggests another. This discrepancy, known as the Hubble tension, is not yet resolved, but if it holds, it could indicate a crack in the standard model of cosmologian opportunity for new physics to emerge. Indeed, we are witnessing a turning point where the questions themselves are evolving. It's no longer just about mapping galaxies or counting stars, it's about understanding the invisible forces that sculpt the entire universe. This shift has led researchers to consider frameworks far beyond traditional cosmology. Some propose that dark energy might be a sign of extra dimensions curled up in the fabric of space. Others believe it hints at a multiverse, where different regions of existence operate under different physical laws. Still, others speculate that dark energy is the effect of quantum fluctuations in empty space vacuum energy with a repulsive push. These ideas are no longer fringe. They are debated in conferences, funded in grants, and pursued in labs. They signal a scientific culture that is not afraid of mystery, but willing to reimagine the architecture of reality in light of new evidence. And underpinning all of it is a technological renaissance. From detectors cooled to near absolute zero, to AI systems capable of parsing massive cosmic datasets, to gravitational wave observatories that listen to the collisions of black holes and neutron star soar, ability to sense the cosmos is accelerating alongside its expansion. But perhaps the most profound part of this turning point is not the data we collect, but the implications we begin to draw. We are entering an era of cosmology where knowledge leads not to certainty, but to deeper wonder. For every pattern detected, there is a mystery unveiled. For every model refined, a new anomaly arises. Galaxies that shouldn't have formed so early in cosmic history, voids larger than predicted, structures that defy randomness. Even the behavior of fundamental particles is being revisited in light of cosmological constraints. As we zoom out further, the lines between cosmology and particle physics, between philosophy and mathematics, begin to blur. And here, in this convergence of disciplines and ideas, the story turns in a deeply human way. We began by asking where the edge of the universe might be. We imagined a boundary, a border, something tangible to reach. But the truth that is unfolding is stranger and more beautiful than anything we envisioned. The universe may not have an edge at all, not because it is endless in space, but because it is recursive in structure, holographic in information, emergent from deeper principles we don't yet comprehend. And in recognizing this, we are forced to reconsider not just the cosmos, but ourselves. Because if the edge we sought is not a location, but a limit of perception, then the true frontier is not in space, it is in understanding. Every telescope we launch is not just looking outward, but inward. Every equation we refine is a mirror held up to the way we think. Every revelation about galaxies or quantum fields or dark energy is a revelation about the mind that asks the question. The turning point, then, is not just technological or scientific, it is epistemological. It is the moment we realize that to understand the universe, we must also be willing to change how we understand. This is the age we live in, an age where we no longer believe the universe is static or small or complete. An age where we can measure its expansion, trace its history, and glimpse its deepest structures, yet still find ourselves standing before questions that humble us. Where does dark energy come from? What is the fate of the cosmos? Is space truly flat or subtly curved beyond detection? Is time a fundamental property or an emergent illusion? And the greatest question of all, why is there something rather than nothing? These are not final questions. They are the beginning of a new chapter, and we are the ones turning the page. With instruments built by international teams, with theories refined across decades, with data gathered from the edge of the observable universe, we are stepping into an era where the known and the unknown coexist not as enemies, but as partners in discovery. The universe, it seems, is not finished with us. It continues to surprise, to astonish, to call us forward. And we, in turn, continue to rise questioning, wondering, reaching. This is the turning point. Not the end of the story, but its transformation. Not the answer to the mystery, but its deepening. And in that deepening, we find not despair but purpose. A reason to look again. A reason to ask more. A reason to believe that even in the vast silence of space, meaning can still be made. For centuries, humanity has tried to understand the universe by reaching farther, seeing deeper, and building bigger machines to measure its vastness. We've launched telescopes into space, mapped galaxies stretching across billions of light years, and tracked the oldest light in the cosmos back to just moments after the Big Bang. With each new advancement, our picture of the universe has become more detailed, more precise. Yet, despite these monumental strides, a growing sense of unease lingers in the scientific community. The questions we once thought we were close to answering. What is the universe? How did it begin? Does it have an edge? seem to splinter into even deeper paradoxes the closer we get to them. At some point, we have to ask a different kind of question. Could it be that we are not failing to see the answer, but that we're asking the wrong question? Could it be that the way we're looking at the universe, through the lens of space and time, energy and matter, is itself the problem? This is where the real turning point begins. Not just in technology, not just in discovery, but in thought. A shift in perspective. A realization that perhaps the universe is not what we thought it was. Not a massive 3D structure expanding into nothingness, but something far more strange, elegant, and elusive. Enter the holographic principle of the most radical and deeply considered theoretical ideas in modern physics. It proposes, quite literally, that the entire three-dimensional universe might be a projection from a two-dimensional boundary, much like a hologram. In this view, everything we perceive as real space, stars, planets, even ourselves is encoded on a distant, lower-dimensional surface, and the depth we experience is an emergent illusion. At first glance, this sounds like science fiction, but it emerges from the most serious work in theoretical physics. In the 1970s, scientists like Jacob Bekenstein and Stephen Hawking were studying black holes and discovered something peculiar. According to classical physics, a black hole's entropy, a measure of its disorder or information content, should scale with its volume. But their calculations showed that entropy was instead proportional to the surface area of the black hole's event horizon, the boundary beyond which nothing escapes. This hinted at something strange. The information inside the black hole wasn't stored in the space it contained, but on its boundary. Physicists Gerard Hooft and Leonard Susskind extended this idea into the holographic principle, arguing that all of the universe could work this way, that the information describing our reality might live on a cosmic horizon, like a vast film strip projecting the illusion of depth. The implications of this are staggering. If true, it could reconcile some of the deepest tensions between general relativity and quantum mechanics. It might explain why gravity is so weak compared to other forces, because it is not a fundamental force at all, but an emergent phenomenon arising from quantum entanglement on the boundary. It could mean that space itself is not continuous, but built from discrete units of information pixels on a cosmic screen, and it reframes the question of the universe's edge. If the three-dimensional universe is a hologram, then asking where it ends is like asking where the image in a mirror ends sits, a misapplied question. The edge isn't in the depth, it's in the encoding. Alternative theories like this are not fringe science anymore. They are becoming central to serious theoretical work, particularly in the fields of quantum gravity and string theory. The anti-de Sitter conformal field theory, ADS, CFT, correspondence, proposed by Juan Maldacena in the late 1990s, provides a mathematical model where a universe with gravity in 3 dimensions can be described by a quantum theory without gravity in 2 dimensions. While our actual universe doesn't match the ADS geometry exactly, this idea has sparked a cascade of insights. It suggests that gravity and space-time themselves could be byproducts of deeper quantum processes, a kind of quantum foam from which reality emerges. But what does it mean to say that reality is emergent? That space-time, the very stage upon which all of physics plays out, is not fundamental? It means that our classical intuitions, distance, motion, mass are, like thermodynamic properties of water, real and measurable, but arising from something else. Just as temperature emerges from the kinetic energy of molecules, space-time might emerge from patterns of quantum entanglement, tiny, invisible correlations between particles that stitch the universe together at the most basic level. In this view, space is not a thing, it's a relationship. And time is not a flowing river, but an ordering of quantum events. This shift in perspective has already begun to reshape scientific discussions. No longer is the universe simply a container filled with things. It is seen increasingly as a network of information, a web of probabilities, a dynamic system of entanglement and emergence. The stuff of the universe is not matter, it is information. Reality, as John Wheeler famously put it, is it from bit. And this changes how we think about everything. The early universe, not a singularity in space, but a transition in information states. The cosmic horizon, not a limit of location, but a boundary of knowledge. Dark energy, perhaps not a force, but an artifact of our emergent space-time geometry. Even the speed of light, long considered the ultimate speed limit, may be reinterpreted in this new framework as a property of the information transfer across the quantum substrate of the universe. Quantum mechanics has always defied classical logic. Particles behave like waves. Observation alters reality. Entangled particles influence each other instantly across distance. But now we are beginning to realize that these are not bugs in the system, they are features of a deeper level of reality that we are only beginning to comprehend. And as we apply quantum thinking to cosmology, we uncover layers of mystery. Quantum fluctuations in the early universe, amplified by inflation, seeded the large-scale structure we see today. Virtual particles in the vacuum contribute to the energy density of space. Quantum tunneling may have allowed the universe itself to emerge from nothing without violating any physical laws. If this is true, if the universe is fundamentally quantum, then the classical idea of an edge becomes even more meaningless. The edge isn't a line we can cross, but a conceptual barrier, a limit in the resolution of our models. Like the edge of a high-resolution photograph, there may be no boundary visible until you zoom in far enough to see the pixels. And in the quantum universe, the pixels may be Planck-scale units of space and time so small that our current instruments cannot even begin to detect them. This is why the shift in perspective matters so much. It changes the questions. It reframes the debate. It says, don't just build a bigger telescope, build a better theory. Don't just look farther, look deeper. Look sideways. Look inward. And with this shift comes a new humility. We realize that the frameworks we've used, Newtonian mechanics, Einstein's relativity, even standard quantum theory, are not wrong, but incomplete. They are lenses that work at certain scales and break at others. And so the challenge is not to throw them away, but to transcend them. To find the unifying narrative that connects all scales of existence from the smallest particle to the entire observable universe. And that narrative may begin not with mass or charge or velocity, but with information, entanglement, and the quantum relationships that underlie the fabric of everything. This new worldview also opens the door to interdisciplinary exploration. It links physics with computer science, mathematics with philosophy, cosmology with neuroscience. The question of how consciousness arises from matter is mirrored in the question of how space arises from quantum states. Both are questions of emergence, complexity, and relationship, and both suggest that the edge of understanding is not out there in space, but right here, at the limits of thought. And yet, for all its elegance, this new perspective is still just a hypothesis, a work in progress. We do not yet have the experiments to prove the holographic principle on a universal scale. We do not yet know how to reconcile quantum gravity with the expanding universe we observe. We do not yet understand dark energy, dark matter, or the full implications of the multiverse. But the fact that we are willing to ask these questions and to consider such radical possibilities is itself a sign of progress. It means we are not bound by dogma. It means we are willing to let the universe teach us how to think. This is the true value of the shift in perspective. It does not give us answers, it gives us better questions. And those questions point to a reality that is richer, stranger, and more beautiful than anything we have imagined. A reality where space is not empty, but full of entanglement. Where time is not absolute, but emergent. Where the universe is not a machine, but a message encoded, projected, and unfolding. And perhaps most profoundly, it reminds us that in the vast silence of the cosmos, the most important shift may not be out there, but within ourselves. To see the universe differently is to see ourselves differently. To accept that our current models may be incomplete is not to admit failure, but to open the door to something greater, something deeper, something closer to truth. And in that search, we find not just knowledge, but meaning, not just data, but insight, not just theory, but wonder. This is the shift. This is the moment. And it is only the beginning. We often think of science as a steady march toward clarity, a clean path from ignorance to understanding, from chaos to order. And while there's truth in that, the deeper truth is more subtle, more tangled. Science is also a story of disruptions, of long-held beliefs shattered by sudden discoveries, of models upended by data that refuse to fit. These moments are rare, but when they come, they leave nothing untouched. They rewrite textbooks, dismantle entire frameworks, and force us to reimagine the universe from scratch. And in the last few decades, we've seen the beginnings of such a disruption, a cascade of unexpected twists that defy our assumptions not just about how the universe works, but what it is. For over a century, we believed we were approaching a theory of everything, a unified explanation of all physical laws, capable of describing the cosmos from the quantum scale to the galactic. But one by one, our most trusted models have begun to crack. The cosmological constant problem, the incompatibility of quantum mechanics and general relativity, the mysterious nature of dark energy and dark matter, and the persistent anomalies in cosmic background data have all conspired to reveal something disturbing, that our foundational understanding of reality may be incomplete, even flawed. That the universe is stranger, more complex, and possibly more layered than we had ever imagined. And among the most shocking of these revelations is the growing plausibility of something many scientists once dismissed as pure speculation, the idea that we are not alone in a single universe, but one of countless universes. A multiverse. The multiverse theory is not a single concept, but a family of ideas that emerges from different corners of physics. In quantum mechanics, it arises from the many worlds interpretation, the notion that every time a quantum event occurs, the universe splits, creating parallel realities where every possible outcome plays out. In cosmology, the multiverse is born from eternal inflation, the idea that inflation never truly ended but continues in other regions of space, creating bubble universes, each with their own physical constants and laws. In string theory, it takes the form of a Lanscapian, almost infinite array of possible vacuum states, each defining a different kind of universe. For decades, these ideas remained on the fringes, intriguing but unverifiable. But then something unexpected happened. Observations began to point to a universe that seems fine-tuned for life in ways that beg for explanation. The strength of gravity, the mass of the electron, the cosmological constant teach falls within an astonishingly narrow range that allows stars, planets, chemistry, and ultimately biology to exist. Alter any of these values even slightly, and the universe becomes sterile. The question naturally follows, why? Why this configuration and not another? Is this sheer coincidence? Divine design? Or does it hint at something deeper, that we live in one universe among many, and we just happen to exist in the rare one where life is possible? This line of reasoning, known as the anthropic principle, has gained traction in recent years, not because it offers comfort, but because it may be the only explanation consistent with observation in a multiverse. If all possibilities exist somewhere, then life will inevitably emerge in some of them. And those are the only universes in which beings like us could ask the question. It's a radical idea, not because it asserts too much, but because it leaves so much open. It replaces certainty with statistics, determinism with probability, and simplicity with scale. In the multiverse, the laws of physics are not universal. They are local. What we call reality is just one patch in an infinite quilt, one bubble in an endless foam. The implications are staggering. It means we may never find a final theory, only a description of our particular cosmic address. It means that questions like, why does the universe exist? Or why is there something rather than nothing? May be undecidable, not because they lack answers, but because they have too many. And it means that our deepest philosophical and theological intuitions may need to be rethought. If creation happens endlessly, randomly, and without purpose, then meaning is no longer written into the fabric of the universe. It must be created by us. But just as we begin to wrap our minds around the multiverse, another twist emerges soon that questions not just the content of the universe, but its nature. The simulation hypothesis. The idea that what we experience as reality might not be real at all. but a sophisticated illusion generated by a computational process. In this view, the universe is not made of particles and fields, but of bits and logic. It is a program running on a substrate we cannot access, created either by a higher intelligence or by natural processes we do not yet understand. This hypothesis is not born from fantasy, but from the strange convergence of physics, mathematics, and information theory. As we delve deeper into the quantum world, we find that reality behaves in ways that resemble computation: quantized energy levels, discrete information storage, non-local correlations. Theoretical physicists like John Archibald Wheeler have long speculated that it from bit that all things physical are ultimately informational. And computer scientists have pointed out that if technology continues to evolve, then a civilization advanced enough could create simulations of entire universes, populated with conscious beings who do not know they are simulated. If that is possible, then the probability that we are in the base reality becomes vanishingly small. This idea is deeply unsettling. It questions not just the structure of the cosmos, but the authenticity of our experiences. It asks whether our memories, emotions, even our sense of self might be artifacts of code, but it also offers an unexpected coherence. Many of the unsolved mysteries of physics, why constants have the values they do, why space is pixelated at the Planck scale, why the universe seems fine-tuned, could be explained if they were design choices made in a simulation. Even the apparent paradoxes of quantum mechanics begin to look like clever shortcuts in a computing system designed to conserve processing power. And yet, as radical as these ideas are, they point to a deeper shift that transcends any one theory. What they reveal is that our place in the cosmos may be defined not by what we are, but by what we perceive. That our models of space, time, matter, and consciousness are not final truths, but perspectives shaped by our limitations. We see in 3 dimensions because we evolved to navigate a 3-dimensional world. We experience time as linear because that's how our brains process change. We believe in a single universe because our instruments are confined to a single light cone. But reality may be far wider, far deeper, and far more layered than our senses suggest. This realization doesn't render science irrelevant, it deepens its purpose. It reminds us that science is not the search for absolute truth, but the quest for better models. It reminds us that certainty is the enemy of discovery, and that true progress comes from challenging assumptions, not defending them. It reminds us that wonder is not the beginning of science, it is its end. When all the equations are solved, when all the particles are named, when all the galaxies are mapped, what remains is the mystery, the vast, open, terrifying beauty of not knowing. And that, perhaps, is the most unexpected twist of all. That the universe, whether it is infinite, simulated, or part of a multiverse, is not something we conquer, but something we participate in. That our consciousness, our curiosity, our creativity are not byproducts of evolution, but essential aspects of reality itself. That the universe doesn't just contain it becomes aware through us. That every time we ask, why? We are not stepping outside the system, but fulfilling its deepest function. We are the universe asking itself a question. In this light, the strange theories no longer seem so strange. The multiverse becomes a reflection of imagination. The simulation becomes a metaphor for perception. And the cosmos, rather than shrinking into determinism, opens into possibility. We are not puppets in a machine, nor accidents in a void. We are nodes in a vast, conscious network. We are reflections of a deeper pattern. We are echoes of a question still being formed. So where does this leave us? It leaves us standing on the edge not of space, but of understanding. It leaves us with paradoxes we cannot yet resolve and visions we cannot yet prove. It leaves us humbled, uncertain, but profoundly alive. Because in the end, the value of science is not that it answers every question, but that it keeps the questions alive. That it invites us to look again, to doubt again, to imagine again. And in that that reaching beyond what we know, we fulfill the most ancient dream of all, not to find the final answer, but to become the next question. Despite centuries of progress, decades of data, and an ever-expanding web of theoretical frameworks. The truth is this: we are still at the beginning. As vast and complete as our maps of the cosmos might appear, they are more like sketches detailed in places, yes, but still surrounded by oceans of blank space and unanswered questions. Every major discovery in modern cosmology, from the accelerating expansion of the universe to the enigmatic fingerprints of dark matter and dark energy, has brought not clarity but deeper mystery. And now, in the early 21st century, we find ourselves at a new crossroads, facing challenges that are no longer merely technical, but philosophical, existential, and foundational to our scientific worldview. The horizon of our knowledge is littered with questions that demand new tools, new ideas, and a new generation of explorers willing to venture into the unknown. If we are to truly understand the universe and not just observe it, we must rise to face these new challenges head-on. First and foremost, there are the limits of our observational technology. As impressive as the Hubble Space Telescope, the James Webb Space Telescope, and the Planck satellite are, they are still bound by fundamental constraints. They can only detect light that has traveled a finite distance, and only within specific bands of the electromagnetic spectrum. This means that no matter how powerful our instruments become, there will always be regions of the universe that are hidden from us, not just by distance, but by nature. The cosmic microwave background radiation, for example, represents a kind of fog beyond which no photons can travel freely. It is the observable surface of the early universe, and while we can infer what came before it through models and simulations, we cannot look past it directly. Furthermore, the expansion of space itself poses a unique challenge. Galaxies are not merely moving through space, they are being carried away by the expansion of space itself. This means that some galaxies are receding from us faster than the speed of light, not by violating relativity, but because the space between us and them is stretching. As time goes on, more and more of the universe will become unreachable, not because it is far away, but because it is forever beyond our causal horizon. This sets a hard limit on what we can ever observe, measure, or verify. It is not a limit of ambition or funding, but of physics itself. To overcome these limits, we need the next generation of space missions that are not merely larger or more sensitive, but revolutionary in design and scope. Projects like the Nancy Grace Roman Space Telescope and ESA's Euclid mission aim to map the expansion history of the universe with unprecedented precision, helping to pin down the nature of dark energy. Ground-based observatories like the Vera C. Rubin Observatory will scan the entire sky regularly, capturing transient events and building a dynamic model of the cosmos. But even these missions are steps, not leaps. The real breakthroughs may come from entirely new ways of seeing: gravitational wave astronomy, neutrino telescopes, quantum sensors that can detect minute perturbations in space-time itself. The next frontier may be defined not by light, but by vibration and mass. Gravitational wave observatories like LIGO and Virgo have already proven their worth by detecting the mergers of black holes and neutron stars events that were once purely theoretical. The proposed LISA, Laser Interferometer Space Antenna mission, will take this further, using space-based detectors to scan for gravitational waves across the entire universe, possibly revealing events from the earliest moments after the Big Bang. These are not science fiction fantasies, they are funded, planned, and in development. And they represent a profound shift in how we explore the cosmos, not just by seeing, but by listening to the vibrations of space-time itself. But even as our instruments grow more sophisticated, the theoretical landscape presents its own hurdles. Many of the most important questions in cosmology: what is dark energy? What is dark matter? How do we unify gravity with quantum mechanics? Do not merely lack answers, they lack a clear framework for answering. Take dark matter, for example. We know it exists through its gravitational effects. We can map its distribution through lensing and galactic motion, but decades of direct detection experiments have failed to find the particles responsible. Is dark matter a WIMP, an axion, a sterile neutrino? Or is our understanding of gravity itself flawed? Modified gravity theories like MOND and TeVeS offer alternatives, but they struggle to match the full breadth of observational data. We are at a theoretical impasse where multiple explanations remain viable, but none are confirmed. Dark energy is even more elusive. We can observe its effects, the acceleration of cosmic expansion, but we do not know what it is. A property of the vacuum? A dynamic field? Evidence of a multiverse? Or something we have not yet imagined? The LCDM model, our current best fit cosmology, includes dark energy as a cosmological constant. But this explanation feels incomplete. The value of the cosmological constant is staggeringly small compared to quantum predictions discrepancy of 120 orders of magnitude. This is not a minor error. It is a gaping hole at the center of our understanding, and solving it may require a radical rethinking of physics itself. To tackle these unanswered questions, scientists are exploring beyond the standard model not just of particle physics, but of reality. Theories like string theory, loop quantum gravity, emergent spacetime, and holography offer tantalizing hints of a deeper structure, but they are still highly speculative, lacking experimental validation. And herein lies another challenge: how to test theories that deal with energies, distances, and dimensions far beyond our experimental reach. How do we falsify a theory that only makes predictions at the Planck scale or in parallel universes we cannot access? The line between theoretical physics and metaphysics is dangerously thin. And yet, to abandon the search would be to surrender the greatest scientific challenge of our time. This is where the philosophy of science becomes a practical concern. We must find new methodologies not just to interpret data, but to define what counts as evidence. We must build collaborations between physicists, mathematicians, computer scientists, and philosophers. We must create models that are not only elegant, but testable. And we must develop tools capable of probing the deep structure of the universe, not just its surface phenomena. Quantum simulations, artificial intelligence, machine learning, all of these will play a role, helping to mine massive datasets, identify patterns invisible to the human eye, and even suggest new hypotheses. And yet, all of this new instruments, new theories, new method hinges on something more basic: a cultural shift in how we approach science itself. We must embrace uncertainty, not as a failure, but as a feature of progress. We must resist the urge to lock onto premature answers, and instead cultivate a deeper patience, a deeper curiosity. The universe is under no obligation to reveal its secrets quickly. It evolves on timescales far longer than human civilizations. And our progress, while rapid by historical standards, is still a flicker compared to the age of the cosmos. We must learn to think not in years or decades, but in centuries. The real breakthroughs may come from scientists not yet born, using instruments not yet built, asking questions we cannot yet imagine. Education and communication will also be essential. As the questions grow deeper, the gap between scientific insight and public understanding widens. If we are to sustain the funding, the will, and the global cooperation needed to push the boundaries of cosmology, we must bring people along for the journey. We must tell the story not as a dry recital of equations and data points, but as the greatest intellectual adventure humanity has ever undertaken. We must inspire not just with facts, but with wonder. Because the hurdles we face are not just scientific, they are human, political, psychological, cultural. We need storytellers as much as scientists, visionaries as much as technicians. And so, the path forward will not be straight. It will twist and loop and diverge. It will demand that we abandon cherished ideas, confront uncomfortable truths, and accept that some answers may remain forever out of reach. But the pursuit itself is what gives the journey meaning. Because in seeking to understand the universe, we are also seeking to understand ourselves, our origins, our future, our place in the great unfolding story of reality. The new challenges of cosmology are not problems to be solved once and for all. They are invitations to deepen our inquiry, to expand our perspective, to become more than we were. So, what hurdles remain? The limits of light and time, the silence of dark matter, the riddle of dark energy, the tension between quantum and gravity, the scale of the multiverse, the boundaries of testability, the fragility of human vision in the face of cosmic complexity. But these are not walls. They are thresholds, and we are not finished, not even close. The stars are still speaking. The data is still coming in. The questions are still growing. And we, standing here with our imperfect tools and our insatiable curiosity, are still reaching forward, still dreaming, still daring to ask the universe what it is and who we are within it. The universe, vast and ancient, has always been both our greatest source of wonder and our deepest source of confusion. For centuries, we've tried to capture it in models, equations, and maps, striving to understand its birth, its structure, and its fate. But even as our instruments grow more powerful and our theories more precise, we find ourselves in the midst of an epic intellectual confrontation that pits competing worldviews against each other, each claiming to decode the truth behind the cosmos. This is the final confrontation of modern cosmology, not in the sense of an end, but of a threshold-in era where ideas clash at the limits of human understanding, and the prize is nothing less than a unified vision of reality. It is the battle of models, of paradigms, of the very framework within which we ask the question, does the universe have a boundary? And if so, what lies beyond it? At the heart of this confrontation are the two great pillars of 20th century physics: Einstein's general theory of relativity and the quantum mechanics that underlies all particle physics. Each theory is breathtakingly accurate in its own domain. General relativity describes the behavior of gravity, space, and time on cosmic scales, predicting black holes, gravitational waves, and the expansion of the universe. Quantum mechanics, on the other hand, governs the microscopic world of atoms, photons, and subatomic particles with uncanny precision, allowing us to build everything from transistors to lasers to quantum computers. But the problem is this: these two theories are fundamentally incompatible. When we try to apply them to the same system, such as the very early universe or the interior of a black hole, they produce infinities, contradictions, and nonsense. Thus, unifying these two frameworks into a single, coherent theory, a quantum theory of gravity, has become the holy grail of theoretical physics. And in this quest, several contenders have emerged, each offering different visions of reality, different explanations for space, time, and the ultimate structure of the cosmos. String theory, for example, proposes that the fundamental building blocks of nature are not point particles, but tiny vibrating strings whose different modes of vibration correspond to different particles. In this framework, gravity emerges naturally as a mode of vibration, and additional spatial dimensions, sometimes as many as 10 or 11, are required for consistency. String theory has the elegance and mathematical depth to potentially unify all forces, but it remains unverified, in part because the scales at which it operates are far beyond what we can test experimentally. Another candidate is loop quantum gravity, which takes a different route by attempting to quantize spacetime itself. Instead of treating space and time as a smooth continuum, loop quantum gravity describes them as composed of tiny discrete loops or atoms of space, woven together into a fabric with quantum properties. This approach has produced fascinating insights, such as a possible resolution to the Big Bang singularity, suggesting that the universe bounced from a prior state rather than emerging from a true singularity. It's a theory that stays closer to known physics than string theory and doesn't require extra dimensions, but it too faces challenges, particularly in describing a universe with the right large-scale structure. Then there is the holographic principle, a concept that originated from black hole thermodynamics but has since grown into one of the most profound ideas in theoretical physics. It suggests that all the information within a volume of space can be described by information encoded on its boundary, just as a hologram contains a three-dimensional image on a two-dimensional surface. This principle, supported by the ADS-CFT correspondence in string theory, offers a radical shift in perspective. Perhaps the entire universe is a projection from a lower dimensional reality. If true, this could explain why gravity behaves differently than other forces, and why space-time itself might be an emergent property, not a fundamental one. In parallel with these theoretical advances, cosmologists continue to debate one of the most basic questions: will we ever find the true boundary of the universe? The very term boundary evokes images of edges, horizons, or frontiers, something final, something measurable. But in the language of modern physics, such a boundary may not exist in the traditional sense. If the universe is infinite, it has no edge, just a continuation beyond our horizon. If it is finite, but unbounded, like the surface of a sphere in higher dimensions, then it has a closed geometry without a true edge. In either case, the boundary may not be something we can ever observe directly. Instead, the universe may be shaped by limits of perception, of causality, and of information, rather than physical walls. This debate is sharpened by data-real, conflicting data. For example, the measurements of the cosmic microwave background by Planck, the expansion rate of the universe as measured by supernovae and gravitational waves, and the distribution of dark matter through gravitational lensing all provide powerful yet occasionally contradictory clues about the universe's large-scale structure. The so-called Hubble tension, a persistent discrepancy between the expansion rate inferred from the early universe and the rate measured in the local universe, has fueled speculation that our cosmological model, the widely accepted LCDM model, may be incomplete or even wrong. As these tensions grow, the community finds itself divided. Some argue for minimal tweaks, perhaps a slightly different model of dark energy, or an unexpected interaction between particles. Others see the cracks as evidence of something deeper, more foundational, a new force, a new particle, a new symmetry in nature, or perhaps a mistake in how we interpret the very fabric of space and time. These are not idle questions, they are the seeds of revolutions. And they echo the scientific revolutions of the past, from the Copernican shift to Einstein's curved spacetime, each one born from the breakdown of an old model. The future of cosmology, then, rests on a balance between theory and observation, between tradition and innovation, between what we know and what we dare to question. On the observational side, next-generation instruments like the Euclid Space Telescope, the Vera Rubin Observatory, and the Laser Interferometer Space Antenna, LISA, promise to map the universe in greater detail than ever before, tracing the distribution of galaxies, the flow of dark matter, and the ripples of space-time itself. These tools will test the predictions of competing theories, help narrow the possibilities, and perhaps even reveal new phenomena we've never considered. On the theoretical side, researchers are diving into unification in unprecedented ways. Quantum information theory is becoming central to our understanding of space-time, leading to the idea that entanglement may literally hold the universe together. Mathematicians are exploring new symmetries and geometries that could redefine how we think about dimensions and topology. And physicists are turning to artificial intelligence to find patterns in data that human intuition might miss, redefining what it means to discover in the age of machines. But perhaps the most important development of all is a shift in mindset, a recognition that the universe may not yield its secrets easily or completely. That some boundaries may be unreachable, not because they don't exist, but because they are encoded in the logic of the cosmos itself. That we are not outside the universe, looking in, but inside it, shaped by its rules and constrained by its structure. And that means our models, no matter how beautiful, must always remain open to revision, disruption, and renewal. This is the essence of the final confrontation, not a war between theories, but a convergence of perspectives, a moment where the walls between disciplines, between cosmology, quantum theory, information science, and philosophy begin to dissolve, where the search for the edge of the universe becomes a search for the architecture of reality itself. And in that search, we are all participants, not just scientists, but thinkers, dreamers, and explorers, each contributing to a deeper understanding of our place in the cosmos. What comes next is unknown. Perhaps we will find that the universe is infinite and that its structure can be mapped with precision. Perhaps we will discover that space-time is an emergent phenomenon, and that the true laws of nature lie in a quantum realm we have yet to decode. Or perhaps we will discover that there are no final answers, only deeper questions, each leading us further into the mystery. But one thing is certain: the future of cosmology will be defined not by what we already know, but by how bravely we confront what we don't. It will be defined by our willingness to let go of certainty, to embrace the unknown, and to recognize that the edge of the universe is not just a place, it is a process of learning, of refining, of evolving, a process that mirrors the very nature of the cosmos itself, expanding, accelerating, always in motion. In the end, the final confrontation is not a conclusion, but a beginning. It is the recognition that we are at the threshold of a new Erewhon where the boundaries between physics and metaphysics, between knowledge and mystery, are blurred. One where the most profound discoveries may come, not from answers, but from the courage to keep asking. And in that asking, we fulfill our deepest role not as masters of the universe, but as its most curious and devoted students. In a universe so vast that even the speed of light is too slow to cross it in a human lifetime, in a cosmos where galaxies outnumber grains of sand, where time itself stretches back nearly 14 billion years, the act of looking up, of wondering, questioning, searching is something truly profound. It's easy to get lost in the scale, to feel small and insignificant, a flicker in the darkness. And yet, the very fact that we can look up, that we do ask these questions, suggests that our place in the cosmos is not defined by our size or power, but by our capacity to wonder. It's in this spirit that the moral takeaway of our cosmic quest begins to emerge. Because exploring the universe isn't just about accumulating data or building bigger telescopes, it's about what that exploration teaches us about ourselves, about the nature of our curiosity, and about the balance between knowledge and mystery. It's about why we explore at all. At the core of every scientific endeavor lies curiosity, not a sterile academic curiosity, but something raw and ancient. The same impulse that led our ancestors to chart the stars with stones and fire is the one that drives physicists today to peer into the early universe using particle accelerators and gravitational wave detectors. Curiosity is not just a trait of scientists or philosophers. It's a fundamental expression of what it means to be human. It's the refusal to accept the surface of things, the drive to understand, to connect, to make meaning out of complexity. And in cosmology, perhaps more than in any other field, curiosity must coexist with humility. Because no matter how far we look, or how deeply we think, the unknown always remains ahead, expanding with every answer we uncover. That tension between what we know and what we don't gives cosmic exploration its moral and philosophical weight. It reminds us that knowledge is never static, never complete, that every equation, every model, every map of the universe is provisional, a step in an endless journey rather than a final destination. And that's not a failure. That's the point. To explore the universe is to accept that mystery is not an enemy, but a companion, something to walk beside, to question, to live with. In this sense, the scientific method becomes not just a tool, but a practice one that cultivates patience, skepticism, creativity, and above all, openness. An open mind is not one that believes everything, but one that refuses to stop asking questions even when the answers are hard or incomplete. This attitude has lessons far beyond science. In an age of information overload, where certainty is weaponized and doubt is often dismissed, the example of cosmic exploration offers a powerful counterpoint. It tells us that uncertainty is not weakness, but honesty. That being wrong is not shameful, but necessary. That the search for truth is not a straight line, but a spirala pattern of refining, revising, expanding. We do not grow by defending what we already believe. We grow by testing those beliefs against the world and being willing to change when the evidence leads us elsewhere. The universe doesn't care about our pride. It reveals itself only to those who listen. In this way, the cosmos becomes not just an object of study, but a mirror way of reflecting on our values, our culture, our civilization. When we send telescopes into orbit or land rovers on Mars, we are doing more than expanding the frontiers of knowledge. We are practicing cooperation across borders. We are investing in the long term. We are betting that truth matters, that the pursuit of understanding is worth the cost. These acts, however technical they may seem, are deeply moral. They affirm a vision of humanity as something more than consumers or fighters or workers. They affirm us as thinkers, as dreamers, as builders of meaning in a vast and often silent universe. And that silence, that cosmic stillness is itself part of the lesson. The universe does not speak to us in words. It speaks in patterns, in echoes, in light and gravity, and quantum probability. It demands that we learn a new language, one made not of dogma but of evidence, one that requires effort and interpretation. And yet, what it offers in return is more than knowledge. It is perspective. A kind of cosmic perspective that shrinks our egos, softens our certainties, and connects us to something much larger than ourselves. When we see the Earth from spaces of fragile blue dots suspended in blackness, we are reminded that borders are illusions, that conflict is temporary, and that we share a single, precarious home. This realization that we are united not just by biology or culture, but by cosmic origin, has the potential to reshape how we relate to one another. All the atoms in our bodies were forged in stars. Every element in our bones and blood came from explosions that lit up the early galaxy. We are, quite literally, the universe made conscious. And if that's true, then our divisions of race, nation, belief are surface level at best. They matter, of course, in the context of history and identity, but they are nothing compared to what unites us. Our shared ancestry in stardust, our shared journey through time, our shared wonder at the unknown. Cosmic exploration teaches us this unity not through slogans, but through evidence. It shows us that we all come from the same place, and that our destinies are linked. Whether we're talking about climate change, technological development, or the future of civilization itself, the questions we face now are planetary in scope. They demand global thinking, long-term planning, and a sense of responsibility that transcends immediate gain. In this context, the universe becomes both an inspiration and a warning. It shows us what's possible when we dream big, when we reach for the stars, but it also reminds us how rare and precious our world is. There is, as far as we know, no backup Earth, no second cradle of life. The silence of space is a sobering reminder that what we have here is unique and worth protecting. This, then, is the deeper meaning of exploring the unknown, not just to answer questions, but to become better stewards of the known, to become more aware of our place, our fragility, and our potential, to recognize that we are both insignificant and miraculous tiny specks in a vast cosmos, yet capable of understanding that cosmos, in part, capable of caring about its fate, capable of building a world where truth matters, where curiosity is cherished, where the next generation inherits not just facts, but wonder. And wonder, in the end, may be the most important part of this story, because it is wonder that keeps the questions alive. It is wonder that fuels the long hours in laboratories and observatories. It is wonder that survives disappointment, navigates uncertainty, and imagines what could be. In a world increasingly dominated by distraction, division, and despair, wonder is a radical act. It refuses to settle for cynicism. It insists that beauty, mystery, and possibility still matter, that there is still more to see, still more to learn, still more to become. In this light, the cosmos is not just a physical space, it is a moral space, a space where values are tested and reshaped, where patience and perseverance are rewarded, where the smallest human question, "What's out there?" opens into the largest possible realization that we are part of a story bigger than ourselves, and that our role in that story is to seek, to listen, to learn, to build knowledge, yes, but also wisdom, to embrace the mystery not with fear, but with hope. And so, the moral takeaway of cosmic exploration is not a lesson with a neat ending. It is a processa lifelong practice of curiosity, humility, and wonder. It is the recognition that even if we never find all the answers, the act of asking transforms us. It stretches our minds, expands our empathy, and deepens our commitment to the truth. It teaches us that ignorance is not a flaw, it is a starting point, and that knowledge, when pursued with integrity, leads not to arrogance, but to awe. In the darkness between the stars, we find not emptiness, but invitation. An invitation to grow, to collaborate, to transcend, to dream. This is what the universe offers us: not certainty, but mystery. Not comfort, but meaning. Not finality, but the eternal beginning of a question that only we, the conscious children of Stardust, can ask, and that is why we explore. Not because we expect to conquer the unknown, but because the unknown calls us to become more than we are, because the search itself is sacred, because the light we send into the void reflects back something beautiful, something human, something eternal. In every great story, there comes a moment when the journey ends not because every mystery has been solved, but because the pursuit itself has changed the traveler. And in the case of humanity's cosmic odyssey, we now stand at such a moment. We've traveled from the earliest myths of star gods and celestial spheres, through Newton's laws and Einstein's curvature of space-time, into the strange domains of quantum entanglement, dark energy, and multiverse theory. We've charted the skies, walked on the moon, listened to black holes collide, and peered into the embryonic moments of time itself. Yet the deeper we go, the more we realize how much lies beyond. Every answer reveals new unknowns. Every model hints at deeper realities. Every attempt to define the edge of the universe only stretches the horizon further. So, should we end this journey with a closed conclusion, a definitive answer? Should we leave it open-ended, as the universe itself seems to demand? The honest answer is that the mystery should remain open, not as a flaw in our thinking, but as a feature of it. Because the mystery is not a gap to be filled, it is a space to inhabit. It is where imagination breathes, where humility lives, where wonder flourishes. In science, as in art, as in life, the most powerful moments often come not when everything is clear, but when everything is suddenly possible. When we reach the edge of our understanding and choose not to turn back, but to lean forward into the unknown. An open conclusion honors that spirit. It resists the temptation of false certainty. It acknowledges that the cosmos is not a riddle to be solved once and for all, but a story that continues beyond the page. And yet, this doesn't mean we've learned nothing. On the contrary, the journey through the universe has taught us more than we ever imagined possible. It has revealed a cosmos governed by elegant laws, shaped by forces we can measure, and filled with structures of astonishing beauty and complexity. We've discovered that the universe is expanding, that time and space are malleable, that matter is mostly empty space, and that most of the universe's mass energy is made of substances we do not yet understand. We've seen that light can bend, that gravity can ripple, that particles can be entangled across vast distances. We've glimpsed the universe not just as it is, but as it was billions of years ago, its birth, its evolution, its unfolding story written in starlight and cosmic dust. Perhaps most importantly, we've discovered that we are part of this story, not separate from it, but embedded within it. The atoms in our bodies were forged in stars. The consciousness that wonders about the universe is itself a product of the universe. We are not observers looking in from the outside. We are participants, co-authors, carriers of cosmic memory. And that realization changes everything. It means that exploring space is not just about rockets and telescopes. It's about identity, about meaning, about becoming aware of the context in which we exist. The more we understand the universe, the more we understand ourselves, not just our biology, but our curiosity, our fragility, our need for connection and significance. And yet, for all this knowledge, the biggest questions remain unanswered. What is dark matter? What is dark energy? Is the universe finite or infinite? Did it have a beginning? Will it have an end? Are we alone? Are there other universes? Does reality itself emerge from something deeper: information, computation, consciousness? Or are we simply projecting our metaphors onto a reality that is, at its core, beyond human comprehension? These questions are not signs of failure. They are signs that we are asking better questions. More subtle, more layered, more attuned to the complexity of the cosmos and the limitations of our tools. And here we must pause and appreciate the value of leaving questions unanswered. Because an unanswered question is not a void, it is a catalyst. It sparks dialogue, experimentation, innovation. It encourages diverse perspectives and fosters collaboration across disciplines. It keeps science dynamic, responsive, alive. If we had all the answers, what would be left to dream? What would drive the next generation to look up at the stars and wonder? It is precisely because the universe withholds its final secrets that we are able to evolve not just technologically, but intellectually, ethically, spiritually. Mystery invites growth. It humbles arrogance. It nurtures wisdom. Some may argue that this open-endedness is unsatisfying, that we should aim to close the book with final answers, to claim victory over ignorance. But the history of science shows us that every final answer is temporary. Newton's laws gave way to relativity. Classical mechanics gave way to quantum mechanics. The geocentric model gave way to heliocentrism, which gave way to galactic cosmology, which gave way to inflationary models and quantum fields. In every era, what we thought was the edge of knowledge turned out to be just a step in a longer journey. Why should it be any different now? So perhaps the greatest lesson the cosmos offers us is how to live with mystery. Not to fear it, not to deny it, but to dwell within it, to let it sharpen our questions, deepen our insight, and inspire our creativity. The universe is not obligated to make sense to us. And yet, we persist. We study, we theorize, we build machines that extend our senses, and we pass that knowledge on. We create meaning, not because the cosmos demands it, but because we do. That is our role, as conquerors of nature, but as interpreters of its song. As we conclude this exploration, it's worth summarizing the biggest takeaways. First, we now know that the universe is dynamic and evolving, expanding outward at an accelerating rate driven by a mysterious dark energy that defies our current understanding. Second, we've identified a vast, unseen scaffolding of dark matter that shapes the cosmos, guiding the formation of galaxies and cosmic structures. Third, we've developed powerful theories that describe the behavior of the smallest particles and the largest structures, but we still cannot unify them. Fourth, we've glimpsed the possibility of a multiverse, of a simulated reality, of a holographic cosmos, and each of these possibilities redefines what it means to exist. But beyond the facts and theories, the true takeaway is the perspective we've gained, the cosmic perspective that reveals Earth not as the center of the universe, but as a fragile oasis in an ocean of darkness. The scientific perspective that shows knowledge as an unfolding process, shaped by doubt, revision, and shared effort. The philosophical perspective that reminds us that being finite does not mean being meaningless. And the existential perspective that suggests that the act of asking, of reaching, of wondering is itself a form of transcendence. And so we return to the question, should this story have a closed or open conclusion? The answer, fittingly, is both. Closed, in the sense that we have followed the arc of discovery to its current edge, and can summarize what we've found with honesty and awe. But open, in the deeper sense that this edge is not an ending, but a beginning. A new horizon, a new question, a new generation of minds ready to take the next step. Because the universe doesn't stop, it evolves, it expands, and so must we. Every unanswered question is a doorway, every mystery is an invitation. And the space between the stars, the infinite silence, whispers to us not of endings, but of potential. There is still so much we don't know. There is still so much to explore. And that, in the end, is the most hopeful truth of all. The story continues.